for inviting me. It's a pleasure being here again. It seems like I come here every year or two and talk about a different disease, and I'll try to keep that pattern for as long as I can, and maybe one or two left. There's an advantage of being relatively late in the program in that some of the stuff I felt I had to talk about, I don't have to. On the other hand, much of the brilliant stuff I was going to say was already said, so it balances out. But what I want to do is talk a little bit generally about vector-borne diseases, vector-borne zoonosis, climate, weather, and anthropogenic change in general, and make some very obvious points, then go talk about the West Nile virus example, and come back to those general points. So, as you know, there are many vector-borne zoonoses. We are talking about West Nile virus, Lyme disease, plague, leishmaniasis, etc. And all of them share the fact that for transmission to occur to humans, four things have to happen. The vector has to survive, the reservoir host has to be present, the pathogen has to be amplified, and finally there has to be opportunities for spillover for transmissions to humans or domestic animals or wildlife of interest. And for all those to take place, it's not that easy. And when we want to talk about what is necessary for it to occur as far as climate goes, a lot of things have to come together for successful transmission to take place. And that includes, it's easy for me to do it. That includes temperature, and as Matt talked very well, it's not just the average, it's the minimum, it's the maximum, it's the fluctuations. The minimum at night is very important for heat effect. Same for rainfall, humidity, extreme events, which are increasingly occurring, are increasingly important. But the point I want to make is that all of those parameters are likely to have a differential impact on the different aspects of vector-borne zoonotic disease transmission. And in fact, they very likely will go in different directions. So temperature may have that kind of an effect on a vector, enhance vector survival, but be very good, bad for the presence of reservoir host. The same for humidity, rainfall, and variability, which means that the impact of specific climate changes or complex climate changes on infection of reservoir hosts and of transmission of disease to humans are very difficult to predict. And not only that, and again, a point that was already well made, is that not only are we talking about climate change, but we talk about increasing climate variability. So trying to predict how those changes will impact the transmission of a vector-borne zoonosis is not a trivial exercise. And of course, we have to talk about the issue of scale, and people have talked about the global resolution level, people have talked about the local resolution level, but both temporally and spatially, we are dealing with factors and their impacts on a range of resolutions going from the interannual to the daily, and spatially from what's happening within a household or between individual hosts, all the way to the biosphere. So the question of how will climate change impact transmission, infection, disease is really a question, at least initially, of how to relate global changes to very complex local processes. And I think Matt gave a good example of how we are trying to downscale those changes, those global factors, in order to explain what is happening locally. But generally, I think we've moved beyond this oversimplified that warmer equals buggier. The idea that if the temperature goes up, we're going to have more disease. And people already talked about malaria. I don't think anybody's talking about dengue today, but several of those diseases transmitted by mosquitoes and by other vectors have been a major topic of discussion for the impact of climate change on transmission. Some of the early work, and this is work on this is a simple prediction of, temperature is going to go up, malaria is going to come back to New Haven, to London, to Copenhagen. Basically, temperature is higher, mosquitoes will do well, transmission will take place. And, relatively early on, this was, kind of rebuked by a nice article by David Rogers and Sarah Randolph, showing that if we look at the biology of the mosquitoes and really understand what derives transmission of malaria, those changes are actually very hard to predict. And in fact, malaria may go up in some places, may go down in other places, but they're not going to be drastic changes in transmission of malaria because other factors are much more important determinants. Lyme disease is another good example. There have been many models, both based on climate and on landscape. Much of the work was actually done by the group here, the group led by Durland and Maria. And there was a model by Brownstein on projected distribution of climate-based, and more recent work on trying to develop a risk model or defining low and high risk areas for the tick for transmission based on a very data-driven model based on the density of infected host-seeking nymphs of ticks. So I want to talk now about our study of West Nile virus in the Chicago area, and then come back a little bit to those general points about climate change, anthropogenic change, and transmission of disease. And this is a study supported by the NIH Ecology of Infectious Disease program, NIH NSF, which really has been a crucial program in supporting that kind of research. Generally, the research that's trying to look ecologically at disease is often too ecological for NIH and too medical for NSF. And I think much of the work reported here actually was supported by this program. So I want to thank them again. This was a collaborative study. I list all the collaborators later. And also it occurs very much on a local level, and it's an urban study. And I think one of the points that I think Mercedes already made, increasingly we need to look at urban areas and at the ecology of urban areas and apply the classical ecological approaches to understanding the urban habitat. So West Nile virus, I think Jeffrey already showed a very similar slide, so I think you know everything about West Nile virus. It came to the US in 1999 from Israel, actually. We know exactly where it came from. And it spread very rapidly throughout the US. And I want to talk about what happened in Illinois, where it appeared in 2001, only in birds, no human cases. In 2002, Illinois had the biggest outbreak of West Nile virus until then. It was surpassed by then in Colorado and recently in Texas. But out of the 884 human cases, there were 884 human cases and 66 deaths. About 25% of all cases occurred in Illinois, and mostly in the greater Chicago area. Then we had two very quiet years in 2003, 2004. We had two active years again in 2005, 2006, which initially thought would match 2002, but they never went as high. And then we had quiet years until actually 2012, where we had 245 cases the last time I checked. If we look at the epidemic curve, this is what happened in 2002, the big year, and then 2005 started out nearly as high, but it never went that far. And there are many reasons for that. I'm not going to talk about them too much, but among them is probably increased immunity among the birds and also better control efforts, because we really learned a little bit about what is effective against Culex pipiens larvae in urban areas. I want to point out that the outbreak years were hot and dry. I'll come back to that in a minute, but that fits some of the hydrological component of the determinant of transmission that Jeffrey talked about. And as an aside, hydrology I found is extremely important, not only for West Nile virus, but pretty much every disease I looked at, whether we talk about tsetse flies or ticks, or snails that transmit schistosomiasis, the hydrology seems to be as important a factor as anything in explaining transmission. So if we talk about the distribution of West Nile virus in Chicago, there were two very obvious foci, and this is Lake Michigan. The loop would be right here. Midway Airport is right here, so one area just south of Midway Airport, and Northwestern University is here. So this is the Evanston-Skokie foci. As an aside, in 1975, there was a St. Louis encephalitis outbreak. Again, Jeff already mentioned it, a disease closely related to West Nile virus, transmitted by the same mosquitoes using birds as reservoir hosts, and the focus here was nearly identical. This is a new focus. One of the questions we haven't really answered yet is, well, this is a really good area for transmission of a mosquito-borne disease, but what changed between 1975 and 2002 that this new focus came into place? I wish we'd be able to answer that. We haven't really yet. So if we look at the distribution of West Nile virus human cases in the greater Chicago area in 2002, again, this is the southern focus, south of Midway. This is the northern focus. One thing that is obvious is that all of this area is in Chicago Lake Plain. It is readily flooded. In fact, this area was largely developed after the Second World War with the baby boom and the big building of houses. When I once presented those slides to some veterinarians in Chicago, they said, oh, we remember this was basically a swamp. Nobody really lived here. So clearly drainage is a problem, means standing water is a problem, means we have good conditions for development of mosquito larvae and transmission. So if we try to do a classification of the urban landscape based on the urban characteristics of housing, vegetation, socioeconomics, and land use, we found out we decided we could divide the urban area into 5 different types. And one type was clearly the area where we had most human cases. We call it urban type 5. Housing developed in the 40s and 50s. Moderate coverage of vegetation, moderate population density. Those are kind of, I would say, blue-collar suburbs. I would characterize those areas. And you can see that really the vast majority of the space was there. There were not many cases in the very, in the downtown area, and not as many cases in the much better forested suburban area. I want to say that much of this work was led by Marilyn Ruiz, a medical geographer at the University of Illinois. One thing that was very interesting that we found out is that around those housing, there were huge numbers of storm drains that nobody knew about. In fact, in the area south of Midway Airport, they found 3,000 of those storm drains in people's backyards, basically. Apparently, there used to be alleys between the houses, and gradually maybe people moved their fences, took them over, they became part of their lawn, and those are perfect habitat for Culex pipiens. I mean, you have standing water, you have grass clippings, you have leaf litter. If you're a Culex pipiens, your larvae, you really cannot ask for anything better. It's as good as it gets. And what happens is that I think hot years are obvious. In hot summers, everything moves much faster. Mosquitoes develop much faster, transmission, amplification, all of that. One of the questions was, why are dry summers apparently more suitable for transmission? And that was the case in the 99 outbreak in New York, and also in the 2004 outbreak in Colorado. I think it was 2004. And one of the things that happens during dry years, especially after good spring rains, and again, coming back to what Jeffrey was talking about, the different patterns of precipitation in parts of the country, you have good spring rains, water is accumulating, and then the water is just standing there. If you have frequent heavy rains in the summers, the larvae get flushed away. So really what you want is dry, hot summers following wet springs. And that seems to have been the pattern, at least in the northeast, Midwest, up to the mountain region. I guess it's different in the Northwest and certainly different in Florida. Okay, so if we want to go a little bit finer and trying to relate the spatial pattern of transmission to very local conditions. Again, the idea is that we really have to understand what is happening locally in order to figure out how those local conditions coalesce to give us the regional picture. So we had many research questions, but 3 of them are, interannually, what are the conditions associated with higher mosquito infection in some years? Within a year, what temporal characteristics of rainfall and temperature precede changes in mosquito infection? And what was the temporal lag? And then spatially, can we use the patterns of rainfall and precipitation to explain differences even within a relatively narrow area? And the work was done in the greater Chicago area, Cook and DuPage County up here. So if we look at the mosquito infection rate, the MIR by week for the 5-year period of 2004 to 2008, and here are, remember, 2005 and 2006 were the years that we had high transmission in comparison to 2004, 7, and 8. What has been noted in every year, actually, regardless of the level of transmission, that amplification of virus occurs relatively rapidly and always around the same time. The last week or 2 of July, the first week or 2 of August is when amplification happens. And that seems to hold, and that seems to be the pattern in much of the country, actually. Again, I don't know about Florida, but it certainly was a pattern in the Northeast, and much to our surprise, it's also the pattern in Atlanta. I'll maybe talk about that briefly if I have time. We know that temperature will affect the speed of the different processes, that pathogens replicate faster, mosquitoes will have a shorter time between blood meals, and in general, that if the winter is warmer, more vectors will overwinter, and that's important because we think that West Nile virus overwinters in mosquitoes. As far as precipitation, provides, good vegetation, provide resting areas for the mosquitoes, provide standing waters, and in general, moisture levels, humidity are extremely important for mosquitoes and other disease vectors. So what we did an exploratory analysis describing the mosquito infection rate and the risk factors, precipitation and temperature. We tried to calculate time lag correlation between degree week precipitation and the mean infection rate. Then we temporarily developed a model to forecast the weekly MIR using weather data, using the year 2004 to 2007 and tested it in 2008, and again more recently. And then spatially, we use regression tree and random forest analysis to develop a spatial model of infection using weather and other environmental factors. So this is, again, our study area. And what we have is relatively rich database for precipitation and temperature. We had the US Geological Survey between 18 and 41 station. We had the Illinois State Water Survey, and we had the NOAA stations as well. So we had relatively good coverage for temperature and precipitation. And then we had mosquito test data based on the data collected by the Illinois Department of Public Health from over 350 traps over the 5 years in the 2 counties. And they collected between 7,500 and 10,000 mosquitoes, 11,000 mosquitoes each year. So what we did is we developed a spatial database. We divide the area into hexagons of 2,100 meters as our geographic units. And for each hexagon, we summarize the weather and the mosquito infection rate and characterize the environmental factors that we knew characterize the urban areas of elevation, vegetation status, housing, age, race, etc. We use them as the abnormal, the difference values for analysis. For example, we looked at the difference between the normal weekly MIR and the observed amount, the difference between the normal versus the observed weekly precipitation, and we found out that the degree week was a good way to use temperature data. And then we use both raw and smooth data for 3 weeks and 5-week average. So what we find out that mosquito infection, and this is the data showing that in 2002, we had a relatively high number of human cases, and the degree week at week 35, which I think is mid-August, was also relatively high. Again, it was higher also in 2005, 2006, compared to the year for which mean infection rate and number of human cases was relatively low. If we try to correlate mosquito infection with cumulative temperature as a degree week, we found out that the correlation was maximized at a base temperature of 22 degrees and a 1-week lag. So really not very much of a lag, actually. As far as prediction, it would be nice if it was later. But when we looked at the degree week difference from average by week, it was very obvious that those relatively high transmission years of 2002, 5, and 6, definitely the difference was much higher than in other years where transmission was much less. So the best linear regression model that we came up with included, other than the autoregressive models, the recent degree week of the temperature and the annual precipitation a year ago, actually. That was the best prediction. We didn't find much with more recent temperature. And in fact, when we developed a mosquito infection forecasting model, it worked pretty well, but it's about 2 weeks in advance. So the question of how useful it is remains to be seen, but at least we feel like locally we are pretty good at understanding what is happening. When we looked at mosquito infection using the observed data and the spatial model estimated data, the model, it's not bad. I mean, when you compare those 2 graphs, We feel like, the infection we predict by the random forest model using all the variables for the same time period was pretty good in predicting it. Again, very short-term prediction. So what we learned is that weekly weather and MIR both varied across the study area and across time, and varied very finely. And I'm a big believer in going to very fine spatial resolution. But at some point and I kind of said, let's go finer, let's go finer. At some point, I feel like maybe we have gone too fine. I mean, I can't make a map that will be as big as fine as what I am mapping. So the question is now, when do we actually stop? What is the optimal resolution that is still useful for us to make prediction, but is not unrealistic as far as collecting the data? We found out that early season dry conditions did not consistently lead to increased infection. That was different than what was observed in Florida. And we found a high correlation between the higher degree week and low precipitation, but that the degree week was the best predictor. And in general, temporally was the most important. Precipitation was more important in explaining spatial differences. What we really do feel that the microclimate, and again, that is echo what Matt was answering, especially in response to a question, the microclimate conditions are really important. The mosquito is experiencing, not what is observed at even the relatively fine net of weather station. It's observing what is happening, in the vegetation, in the pool, if it's a larvae, under the tree, etc. So we really have to, and we found also this high degree of variability, even in virus genetic characteristics, over a very fine resolution. So again, I'm stuck with the questions of how fine we need to go. I thought this slide was actually appropriate because somebody talking about, what is happening to the weather. So this is one prediction by somebody from the Illinois Natural History Survey. What will be the weather in Illinois in the end of the century? It will be more like Texas. So that was kind of funny to see. Okay, so this is a study that was done by a lot of people. It's the second EID grant is led by Tony Goldberg from University of Wisconsin, Ned Walker from Michigan State University, Marion Ruiz from University of Illinois, and a large number of other people that have been part of this study. I don't have time to talk too much about what is happening in Georgia. But in Georgia, since I moved there in 2008, I figure let's go on and look at what's happening with West Nile virus in Georgia. And one of the big questions, and it's still a big question, why is transmission in Georgia so low? In fact, until this year, the question was, why is transmission in the South so low? I think most of us in West Nile virus came to the US, and you've asked us to predict where it will do really well. You probably would have said New Orleans, Miami, I don't know, Montgomery, Dallas, etc. That has not been the case. Of course, this has changed because this year we had this really big outbreak in Texas, more than in Dallas, more than anywhere, more than ever before. But that did not happen in Georgia, did not happen in Alabama. So still, I don't know what is the matter with Texas. But that one is really kind of. And the one thing I want to say is nobody, to my knowledge, predicted that. People have been trying to develop models for West Nile virus and how it will do in different countries. I haven't heard of anybody saying there'll be a lot of West Nile virus in Texas this year. Of course, now we have reasons to explain it. I have heard people say that the weather in Texas actually was relatively comfortable this year, while the weather in Chicago was not. So actually, it was about the same temperature in Chicago, which means everybody in Texas went out and celebrated, and everybody in Chicago stayed home and wouldn't go out. But that's a retroactive explanation. So what happened in Georgia is that we never had more than 60 cases per year in compared to the 800 that we had in 2002 and the over 200 that we had in 2006. M5, 6, and 2012. So we don't know what the answer is. In fact, that's one of our main research emphasis is trying to explain what is different in the Atlanta area. And we have some ideas. It's not the mosquito infection rate, and it's not the bird infection rate. So it's really the spillover to humans that does not take place. Initially, I thought it's the mosquitoes. That would have been the easier. That didn't work. So we started trapping birds and looking at birds. That didn't work either. In fact, we find level of infection in birds that is comparable to what's happening in Chicago, even in high infection years. So the spillover to humans does not take place. When I moved to Atlanta, it occurred to me that the canopy seems to be relatively high. There's not as much canopy on the intermediate and low level. There's a lot of trees which have the canopy very high up, and maybe there's a lot of transmission happening there, and it's not spilling over down to the lower levels. Maybe the diversity of avian hosts. I don't know how important the different climate and weather is in Atlanta. So it's hard. We don't have the answer just yet. We have some ideas about that, but it's still a little bit of surprising. Okay, that's what I want to say about West Nile virus. I want to come back and make a few points about generally about climate and anthropogenic change and transmission. I said there are many examples that people talk about the impact of climate change: malaria moving up the highlands in sub-Saharan Africa, malaria returning to temperate zones, dengue spreading north and south, especially in America, introduction of Rift Valley fever or chikungunya into the US. Chikungunya already was introduced into Italy once, and there have recently been 2 papers, modeling papers showing that claiming there's a high probability of chikungunya. If it makes it to the US, it will spread very well in Atlanta and maybe even in New York. Blue tongue has moved up north in Europe, although some people say that it has really nothing to do with climate change. And there's a large number of other, non-vector-borne diseases that are likely to be highly impacted by change in climate and by change in other anthropogenic change. And really, that's the point I really want to, make for a few more minutes before I finish, is that it's really human population growth that is a single driving factor at all scales. I know it's obvious, but I think we talk about climate change, we talk about urbanization, we talk about habitat fragmentations, about deforestation, so reforestations, a lot of, increased globalization of commerce and movement, and all of those things really relate to the fact that, that we have, more people, and they directly impact also where they live. The fact that we have so many people living in coastal areas render us much more susceptible to the impact of climate change, especially extreme events. So to understand the impact of anthropogenic changes, including climate change, on this transmission of vector-borne zoonotic diseases, I kind of echo what Matt was saying. There's a lot of stuff we don't know yet. In fact, one of the things I say is if you really want to make predictions about climate change and transmission of a vector-borne zoonosis, do we really understand how weather is impact the behavior of the mosquito? How vectors impact the behavior of the reservoir host or the development of the virus or the protozoan that we are looking at? We really have, I think, to know much more about those before we make predictions about how changes in climate, including the complexity of those changes, will impact something as complex as transmission of a vector-borne zoonosis. So we really need to get better at assessing vector and reservoir populations. We need many, we need many more long-term study. When West Nile virus came to New York, everybody said it was a good year for mosquitoes, but there were no data whatsoever. In fact, there was no mosquito in surveillance, I think, for over 20 years in New York. And after West Nile virus, suddenly there was some more funding for surveillance of mosquitoes and mosquito-borne diseases. And I think, I'm sure as Ben Beard can testify, that died down as, they kind of got used to having West Nile virus, So in a way, West Nile virus was a nice opportunity. It's a relatively not a very serious disease. It has impact, but compared to Rift Valley fever or others, it's not that serious. It was a perfect warning call for us to really, get our surveillance system going, support this kind of long-term research, but that hasn't really happened, which is part of human nature. We don't know enough about pathogen transmission dynamic. We need to consider also multi-parasite systems, and I think that is actually changing. People are realizing that rather than study a single parasite, it makes sense to study polyparasitism, and that is actually, to me, an exciting development. We need to consider the spatial and temporal scale heterogeneity. We need to better, that's obvious. And in general, I think we have to better understand the unchanging associations between climate, landscape, weather, and the complex components of vector-borne zoonotic diseases. And again, I think Two people already showed the vectorial capacity, but that's one example. I mean, do we really know, can we really measure, do we really understand how different components of climate and weather will impact the different terms of the vectorial capacity: population size, blood feeding habits, survivorship, vector competence, and then for the pathogens, how they'll survive and amplify, human socioeconomic factors, reservoir hosts. We actually don't really have an equivalent equation to the vectorial capacity for the reservoir capacity. There are some, but we are not there yet. And of course, the actual transmission between the vector reservoirs and the spillover to humans. So I think some key questions that remain unanswered is, what will be the impact of climate change and variation on vector and reservoir population and on exposure? And are those relationships universal? And if not, how do they vary locally? And how can we assess and incorporate the heterogeneity of scale in time and space? So the real question is how to better apply climate data and models to transmission studies and disease management system. And the conclusion, I think I already said that climate change can work in both ways, but other anthropogenic changes are equally important. And we really have to interpret modeling studies cautiously before they're used to forecast changes in vector and host population. And I think I'll leave this on and I'm done.